So, what exactly is coding? It's not that fabled ones and zeros that everybody thinks it is. It's a little bit different from that. Sure, on the lowest level of what programming is, it does get broken down into ones and zeros. But for most coding situations these days, it's something that's a lot more easier to read and closer to a spoken language. What coding actually is it's just a set of instructions that is written out in a way that the computer can understand. So you can write the same thing as like a sentence. Um, a sentence has syntax, it has certain wording, it has a format to it. Coding works the same way. But with that sentence that you're writing code, it then gets compiled or turned into a machine language that the computer can understand. Probably the most basic way to put it is that it's just a set of instructions. You could compare it to making cookies. You can just have a regular recipe for making cookies, and as long as you follow that recipe every single time, you'll have the same result. The computer takes that one step further, takes those instructions and does it exactly the way you specify. Whereas as a person possibly making cookies or following a recipe, might add a few more chocolate chips or maybe less butter. A computer will do exactly the way it's told to do it. So if you don't complete those steps properly, let's say with cookies, you forget to add sugar, those cookies are probably not going to be too sweet. For a computer, if you don't add sugar, it's pretty, if you have a wrong line of code, not only is that not going to be too sweet, it won't be able to compile, or there'll be what you call a runtime bug, which is the code might crash the program, or it won't do what you're looking to do with the code. So yeah, the big things here are that they're just instructions. It's not as crazy as people expect it to be. It's also not as math heavy as people expect it to be. You're not doing advanced calculus expressions or finding derivatives or anything like that. It's a lot more logic heavy. So you're breaking it down in the simplest steps on how you can do something and then converting that to a language the computer can understand. No matter where you go in the coding world, there are about 3 different elements that branch through the whole entire thing. It consists of variable types, which are usually like integers, or chars, which would be letters. You can go even further with that. You can have things like strings, which would be like a sentence or a word, or a strung together bunch of characters, probably where the name came from. And then you have different kinds of numbers there as well. But there we have the variable types, and then we also have decisions, which would be an if-else type of decision, and we have loops, or iteration. You can look at the variable types as your ingredients. So your eggs, your butter, your sugar, your flour in the cookie recipe. And the decisions and the loops are kind of more set on the instructions. So in one case, let's say you didn't have butter. You started mixing all the ingredients together and you go through your fridge and you find out that you do not have butter for this recipe, but you do have vegetable oil. You can replace the vegetable oil with the butter. That's an if statement. So if you don't have butter, use vegetable oil. So in the words of a computer, this is a decision, a branch that it can make based on information you're given. The information that you're given is you don't have something that you need, but you have an alternative that you can go to instead. A iteration or a loop would be like doing something over and over again for a set amount of time. So if you have to put eggs into your cookie dough, you are instructed to crack 2 eggs into the bowl and add it to the mix, you have a loop of cracking eggs. So you have the first egg you crack, you put it in, then you crack the second egg, you put it in, and the loop is over. Pretty much every language you work with is going to have some form of decisions and loops, because that's the main things that computers work on. You give information, it makes a decision based on that information, and then it loops through that information if it needs to. And you also have all these different variable types that you have exposed to. On a higher level language, which would be something like Java or C++ or Python, you have very set words that you use to declare these types or use these types of things. Whereas on a lower level, it's a little bit more difficult. If you have something like assembly, which actually does use ones and zeros, it's harder to get exactly what you want. It is possible, but you have to jump through a few more loops and you have to do a few more things to get things that you want. Whereas with like something like Java or C++, it's been designed to be a lot more user-friendly and readable. This right here is just a little snippet of code. I wanted everybody to see what it actually looks like. So in this case, we have a variable being declared, we have an if-else statement, which is a decision, and we also have a loop in there. We have specifically a for loop. This code isn't really doing anything special, but it is just the building blocks of what everything is built on when it comes to code. On the first line here, we have int x equals 5. That's declaring a variable. We're calling the variable x, and we're setting it equal to 5. After that, we have an if statement. We're making a decision. We're saying if x, which x is equal to 5, is less than 10, then you're going to do this next block of code, separated by these curly brackets. What this is checking to see is inside the if statement, inside those parentheses, is this true? If this is true, then the code goes through. If it's not, it goes to the else. In this case, x is less than 10 because x is 5. It will go through this code, and now it'll check for this. This is called a for loop. We have int I is now equal to 0. Now we're saying if I is less than 2, then we're going to go through this loop. And then at the end of the loop, we're going to increment I by 1, I++. And what this will do, it will print out 1, and then it will print out 2. Because we'll print out 5 twice, my mistake. It will go through twice, and it will print out 5. Because this is a print statement, it will print to the console, and it will print out x. X is 5, it will go through. Print out twice, because this is true. If it's not true, it will go to the else, and it will only print out once. Everything in coding is kind of built on these 3 structures. When it comes to different languages, there are a little bit differences. Like with Java, you get more into objects, and that's a hierarchy of code rather than just a straightforward procedural programming, something like C. But with C and with Java, with C++, you can have a very similar set of code right here, and it would do pretty much the same stuff. There's, very small differences between the two when it comes to the actual coding. But as you go through it, once you learn one, it's easy to understand and learn another language. So beyond just the basic parts of code, one thing that's really come into play in the last probably 15 years, and probably thanks to Apple a lot, is aesthetics have really changed the game on software and coding. The main goal for coding is to make sure that your computer and your software can complete a task in the most efficient manner and also does not have any bugs or errors. But as we've moved on, that's become more common to have very complete programs and also well put together software, that we need an edge on everything else. We need to make sure that people want to use our software. So here's where aesthetics come into play. every screen that you see, every menu that you see, any design that you see on your phone, on your computer, on your tablet, that has all been designed by a team of people that want to make the best experience for you. Sometimes it doesn't feel that way, and sometimes it actually does the opposite. But there are people who research the best way to get you to want to use the software that they're making. And I brought up Apple because Apple has done that a lot. They've done a lot of marketing towards their product, whereas their software and their the actual devices might not actually be the highest specs, might not actually be the most powerful machine you're getting. They made sure to make it slick and make it appealing to people to want to think that it actually is a lot better than it actually is. But if you cannot sell your software, people won't use your software. So in this case, aesthetics really do matter. Every button and every color that's placed on your device in a certain way was chosen to make you want to use it better. And also, as we go on, and if you look at older software, even from 10 years ago, stuff starts to look dated fairly quickly when it comes to the technology world. People want both change, but not too much change. So if you grabbed a phone for every year from 2010 until now, you can see a progressional change of the UI, of the user interface, of the experience you're getting, but it's a gradual one. It's not one that's just immediate change. Here's one of my favorite topics that we'll be going through, and it's just video games. Video games probably get a bad rep for being just entertaining. But on the other side of stuff, the people that have to make the video games, it's a very difficult process. And I've been through the process before. I have made a few video games myself. As much as I'd like to say it was a fun experience, it's hard to really explain how much work goes into one simple video game. You have to think about more than just the way that the game works. So, as we were just talking about aesthetics, people want to see a well-made game, and they also want to see a game that looks nice. Graphics are very important. As we've gone through time, graphics have improved drastically. Over the past 20 years, over the past 30 years, actually, we've seen a huge change in graphics and what computers can handle. And that turns into it being kind of an arms race of figuring out what to do next. You also have to bring in components of making sure your game actually works properly. It's one thing to have this game that looks beautiful, but if it doesn't work, if there's tons of bugs, if there's glitches, then people aren't going to want to play it either. The other thing you have to worry about too is making sure that you have a good story, that people are compelled to play it. There's different types of games for different types of people, but it really is where technology is going to meet art, is going to meet storytelling, and it's going to combine in this one medium that cannot be expressed in anything that we've seen before. And it's evolved as we've gone through the years. I would say that you also have to figure out gameplay as well. You want to make people want to play the game. You want to make sure people have a good time, and it's hard to judge fun. What really is fun when it comes to technology and gaming. The amount of code that goes into these games at the end of the day is ridiculous. We saw some code earlier. We saw that snippet of code. That's only about 10 lines. We're talking about hundreds of thousands of lines of code just to make sure somebody's entertained. And not just that, but the market for video games has been extraordinary in the past 20 years. If you make a game that does well, the amount of accolades that you can get from that, as well as putting your name out there, even if you were just working by yourself, could be extraordinary. So in the sense of, what's the best game out there or anything like that, that's all opinionated, but one of the most highly selling games to this day is Minecraft. And the reason why I bring up Minecraft is because Minecraft, while I think it sold for over $1 billion to Microsoft, it started out with just a team of 7 people. And not only did it start out with a team of 7 people, it started out with just an independent team of 7 people. So it didn't have a huge company backing it or anything. It was just a group of people that wanted to make a game. And the game was made in a language that games aren't usually made, which is Java, which is where that snippet of code that I showed you before came from. So those building blocks that we just saw was able to make this game that's become so popular throughout the years and has made a lot of money for people. It's the same language that I know very well. It's the same language that I teach. But it's up to you. It's a sandbox of what you want to do with the code that you're given. And for the last kind of bit, I just want to go over this game called Connect 4. I don't know if I've realized teaching international students, it's not always the same game throughout the world, but it's a basic board game, usually designed for children. We can see the instructions down here, but I have the next slide that will go over it. And then we also have this nice little animated GIF to show you how the game's played. The point of the game is you drop these tokens into this vertical board, and you want to connect 4 pieces of your color before your opponent can. And it's just a turn-based. You go back and forth, dropping one in. Whoever connects 4 first wins. Very basic game to understand face-to-face as a person. It's a very basic game to learn and play. I think usually you can have like a 4-year-old play it. They probably won't play it too well, but they would be able to get the basic concept of the game. This is a game that's completely possible to code in a computer language. However, it gets a lot trickier than you think, because as you go through this game, you have to go step by step, and you have to think about the process of what the computer actually has to do. So I know for a fact that if I put 4 in here and I connected, you can visually see who's won. It gets a little different for the computer because the computer has to check every single step. So after every move, as a person, you're not going to look at the board and go, did I win? Did I win? Did I win? Did I win? No. But the computer has to do that because the computer doesn't really understand what this game is. It doesn't have this abstract thinking of what it's trying to do. You're just giving it a set of instructions to do. So it has to understand, all right, if I pick the first column, it has to drop the token all the way down to the last spot that isn't chosen already. It also has to understand whose turn it is. And then after each turn, it's going to check to see if there's a winner. It will check every single spot in some cases of code to see if there is a winner there yet. Even if you know visually that these spots are empty, it will check to see if there could possibly be a winner each turn. And then finally, once there is a winner declared, the game has to end in some form. Every single step of that game has to be accounted for in order for this to work for a computer. So that's just a basic board game that many people have played, or it's very similar to tic-tac-toe. You can only imagine how much work would have to be put into something, more advanced than that. Any more advancement to that game, or even another board game like Monopoly would be a huge step above on the stuff that you'd have to code for that. I usually give this assignment to my students every year. It's a very impressive assignment to work on. There's a lot more components on the back that they have to learn to figure out how to do it. And then on top of that, you also see the aesthetics come into play because I do make them have a graphic user interface that comes up to show this kind of board. And what you see is each student does it a little bit differently. Their games don't look the same. They all have personalized touches to it, which is part of the process of creating software as a whole. And to just kind of throw it out there, A game like this, on average, I went through some of the students' code, was about 1,350 lines of 1,350 lines of code, which is a decent amount of code. It's not a lot of it when it comes to like a larger software system, but just for a basic board game, this is a lot of code for what you need for something like that. But pretty much that wraps up what I wanted to go over for today. Just a very brief overview of where coding can go, and how it connects with other uh, situations in life when it comes to art or storytelling or gaming, anything else. Technology is branching out in every aspect of our life, and won't really be going away anytime soon. So I thank you all for joining me today. I really appreciate that you guys are here. I hope you got something out of this. So thank you. So I have a question. How is the software that makes the software made? That's actually a great question. It gets a little tricky when you get down to the basic parts of it. Essentially, it's a chicken before the egg type of question that you're asking. So first there was machine language, and then as we go on through the years, the machine language was able to create other languages from it. You use other languages to make new languages in some cases, or the basic level language like a machine code, which is closer to that ones and zeros, to make a different programming language. Those kind of things are a little bit deeper on the computer science scale of stuff rather than on the surface of just coding and programming. But I do appreciate that question. That is a tough question to answer and also a very good question to ask. So a bug is something that's either known as, there can be two types of bugs. One bug would be a compiler error, which would be the computer can't actually run the program at all. It can't compile to a machine code, which means the computer won't be able to understand, and the software just crash automatically. Now another kind of bug is one where your software runs correctly, but it doesn't do what it's supposed to do properly. You'll see bugs in like video games where you have a boss that won't take damage. There's something that wasn't accounted there, that something wasn't connecting and that was supposed to happen, but it didn't. Which that means is somewhere in the code, it was logistically not done correctly, so you result in a bug.